This video is on oxidation-reduction reactions, also known as redox reactions. So a redox reaction is a reaction that involves a transfer of electrons, and therefore substances will undergo a change in their oxidation number. So there's oxidation rules that we need to know. Our oxidation number is a reflection of how an element in a compound or ion is controlling its own electrons. So you'll remember that when we learned about bonding, we looked at the periodic table and we saw that magnesium has a charge of +2, fluorine has a charge of -1, oxygen has a charge of -2. Okay, those are called oxidation numbers. We called them charges. Okay, those are interchangeable. And we're going to look to see if we have an element in a compound, we can do a little elimination and strategy to figure out what are the oxidation states of all the species in that compound. If we look at a shared covalent bond, the more electronegative element's going to control both those bonding electrons. So if we think of water, we know that water has the oxygen in the middle, hydrogen, hydrogen, and we talked about earlier how our oxygen has this 2 lone pair of electrons. Remember, we can kind of imagine that there's an electron on either end of this bond being shared back and forth. And we said, well, oxygen really pulls hard on this electron to pull it close to it. And same thing here. So that gives oxygen that partial negative charge, and then those hydrogens that partial positive charge, which is the reason why water can break apart those ionic compounds. Well, the more electronegative element in water is oxygen, thus it controls those electrons more because it has that electron desire to have those electrons close to it by its electronegativity. So some rules for assigning oxidation numbers. So an atom or an element has an oxidation number of 0. So that's like sodium, your diatomics, right, because that's the elemental state that they want to be in. O3, which is ozone, mercury, right, sodium. Anything we find on the periodic table is going to have that oxidation state of 0, which makes sense, right? It doesn't have a charge, it's just the atom. Then a monatomic ion is the same as its charge. So it'd be the charge of the ion. So if we see sodium +1, chloride -1, they're going to automatically have those charges. Fluorine is one that's always going to go a certain way. Fluorine is -1 in all of its compounds. So here, if I'm looking at hydrofluoric acid, fluorine's going to have a charge of -1. Same thing here, fluorine has a charge of -1. Here I have 3 fluorines, so they're going to give me a total charge of -3, so -1 for each one, which means phosphorus here, to balance it out, would have to have a charge of +3, and hydrogen here would have a charge of +1. So remember that we want our compounds to be neutral. Right, they have to get to 0, and that's going to help us figure out the charges of other things. Oxygen is usually -2 in its compound, except when we have peroxide, which is that O2 with a -2 charge. In that case, oxygen has a charge of -1, which makes sense because if this whole thing is -2 and there's 2 oxygens, each oxygen had to contribute a -1 charge. But every other time, oxygen is always going to be -2. So if we look here, if oxygen is -2, that means that hydrogen has to give a total charge of +2, and there's 2 of them, so every hydrogen is +1. And then here, oxygen has a charge of -2, but there's 2 of them, so that gives me an overall charge of -4. So that means that carbon here has to have a charge of +4 to balance out my molecule. Hydrogen is always +1 in covalent compounds. So hydrogen's +1, so if we look here, like we did with water here, oxygen was -2, hydrogen was +1. Here I know that hydrogen's +1, so chlorine must be -1. Here I know hydrogen is +1. There's 3 of them, which gives me an overall charge of +3 from the hydrogens. So nitrogen here must be -3. Okay. These are things that you should remember. It'll be really helpful while you do your redox reactions. So let's explore a redox reaction and assign oxidation numbers. Here we have magnesium solid. That's my elemental form of magnesium. So that has a charge of 0. Here I have oxygen. It's a diatomic in its elemental form, so that has a charge of 0. And then I have magnesium oxide. Now these are in compounds, so I have to do a little calculations to figure out my oxidation numbers. So I know oxygen is always -2, and I only have one of them. Overall, my charges for my molecules, or for my atoms and ions in my molecules, need to total up to 0. So magnesium must have had a charge of +2. That means if I look at my individual species, magnesium is going from magnesium 0 as an element to magnesium +2. And then oxygen is going from O2 as an element to O -2. So our different elements are changing in oxidation number, and that's going to let us know, this path of electrons is going to let us know if we have something called reduction happening or oxidations. So we remember that electrons have a negative charge. And if I gain electrons, that means that I'm going to become more negative. And if I lose electrons, I'm going to become more positive in my charge because I've lost negative things, and therefore I have more protons than electrons, and I have that overall positive charge. Okay, so here magnesium has gone from 0 to 2, so it has lost electrons. Right? If it lost electrons, we're going to find out that it's been oxidized. And if it gained electrons, like oxygen gains electrons, becomes more negative, it's going to be reduced. So 2 new terms for us to learn. We have oxidation, which is an increase in oxidation state or a loss of electrons. So we become more positive. Reduction is a decrease in oxidation state, a gain of electrons, and that is more negative. So if we look at our example here, magnesium to magnesium +2 lost 2 electrons. So if it lost electrons, it's oxidized. Okay. Oxygen here went from 0 to -2, became more negative. It gained electrons, 2 electrons. So we say that oxygen was reduced. Okay. Now we can have an oxidizing agent and a reducing agent. The substance that accepts the electrons is itself reduced, and then the reducing agent is a substance that donates electrons, itself is oxidized. So if we go back up here, we notice that magnesium lost 2 electrons and oxygen gained 2 electrons. So them coming together, 2 electrons came from the magnesium and went to the oxygen. So magnesium lost 2 electrons, they were given to the oxygens, and that's how this ionic compound was formed. There are 2 different strategies to remember if something is oxidized or reduced. You could say oil rig or Leo Gur. I like Leo Gur better. So Leo the lion says Gur, right? But you can do either way. So oil rig is where they say oxidation is lost, so like a loss of electrons. Reduction is gained, so the gaining of electrons. I like to think about it using Leo Gur, where if you lose electrons, you're oxidized, and you gain electrons, you're reduced. So if we go back here, again, just to use that acronym. So if we use Leo Gur, lose electrons, oxidize. So magnesium lost 2 electrons, it's oxidized, whereas oxygen gained electrons reduced, gained 2 electrons, it was reduced. Same works with oil rig, so oxidation is lost electrons, so lost electrons is oxidation. Reduction is gained, so reduction is gained electrons. Either way. It's important to note that when electrons are transferred, it is critical that charges balance, okay? And that electrons lost must equal electrons gained. So we can't, just like our law of conservation of mass, we can't destroy mass, we can't destroy our electrons. So now let's go ahead and go through a reaction, a redox reaction. There are steps, balancing equation steps that we're going to follow. So if you want to have these out next to you or you want to write these down, these are the steps that we're going to follow as we go through balancing a redox reaction in an acidic solution. So the first thing that I go ahead and do is I'm going to write out my oxidation numbers for all of my species in my equation. So here I have an ion of hydrogen, so that's going to have a charge of +1. Hydrogen has a charge, we said, oops, this should be O7, oxygen 7, O7. So oxygen has a charge of -2. There are 7 of them, so it gives me an overall charge from the oxygen is -14. My total charge of the ion has to be -2, so I need to have 2 more parts negative than positive, so my positive parts have to be +12. That must come from my chromium. I have 2 chromium, a total charge given of +12, so that means my chromium has a charge of +6. Here for my alcohol, I have oxygen always with that charge of -2. Hydrogen with the charge of +1. So here +1 gives me +5. So overall with my known atoms, I have 1 minus 2 is -1 plus 5 is -4. So that means my carbon has to give a total of -4 charge. If I have 2 of them, so that means each one gives me a charge of -2. Chromium is an ion, so that has a charge of +3. Carbon dioxide, oxygen I know is a charge of -2. I have 2 of them, so that gives me an overall charge of -4. That means carbon must contribute a +4 charge here to balance out my molecule. And then water, oxygen has a charge of -2. Hydrogen must contribute a total charge of +2, and I know that each hydrogen is +1. So if I look here, I have some species that are changing the oxidation state and some that are not. So my hydrogen goes from +1 to +1, so I don't have to worry about that one. My chromium goes from +6 to +3, so I make +6, +3, so that one's changing. And my oxygen is staying the same every time, so I don't have to worry about that. Same thing here, oxygen stays the same, hydrogen staying the same. So then I check my carbon. My carbon's going from -2 to +4. So -2 to +4. So that means that one is also changing. Okay. So then I'm going to write a half reaction. A half reaction is like what we did before with the magnesium oxide. I'm going to pull out my 2 changes in electrons. So my first one I have is dichromate, -2. So my chromium's changing, and the other half of my chromate is my chromium ion. So that went from my charge of +6 to +3. So I like to write my charge in above it. My other half reaction is my alcohol going to carbon dioxide. So my carbon going from -2 to +4. So I'm going to write down here my other half reaction. My C2H5OH going to CO2, where my carbon's going from -2 to +4. Okay. My first thing to do for each half reaction is to balance all the elements except hydrogen and oxygen. So those are usually the ones who are doing the actual changing in oxidation state. So here my ones that are not oxygen and hydrogen are chromium. I have 2 chromiums here and 1 here, so I'm going to add a 2 in front. Okay, I'm going to do these one reaction at a time. After that, it says to balance the oxygens by adding water units to the side needing oxygen. So this side has 7 oxygen, this side doesn't have any. Every water molecule gives me 1 oxygen, so I need a total of 7 waters. Then I'm going to balance the hydrogen by adding H+ units to the side needing hydrogen. So on this side here I have no hydrogens, and this side I have 7 by 2, which is 14 hydrogens. So I'm going to add 14 hydrogen ions to my left side. So right now I have 14 hydrogens here, 14 here, 2 chromium, 7 oxygen, 7 oxygen. Okay, so my reaction's balanced except for my charge. Right now my charge of my chromium is +6 here and +3 here. So I need to balance the charge on each side by adding electrons. Each chromium here goes from +6 to +3. So each chromium needs 3 electrons to balance out the charge from +6 to +3. So since I have 2 chromiums, that means that I need to add a total of 6 electrons to my side on the left. So my 6 cancels out with my 6 here, which is really 12, to make this oval all +3. My next one, I'm going to follow the same steps. So I have here 2 carbons and 1 carbon here. Two carbons here, 1 carbon here, so I'm going to balance my non-hydrogen oxygen elements first. So I add a 2 here. Then my next step is to balance my oxygens by adding water. I have 1 oxygen here. 2 times 2 gives me 4 oxygens. So I'm going to add water to my left side. And to balance that, I need to have 3 oxygens coming from my water, so I have 3 plus 1 to be 4. Next, I'm going to balance my hydrogens. To balance my hydrogens, I'm going to add hydrogen ions, so H+, to the side that needs some. So I have 3 times 2 gives me 6 hydrogens here, plus 5 is 11, plus 1 is 12. So I'm going to add 12 hydrogen ions to my right side. Now I'm going to balance the charge on each side by adding my electrons. On my left, my carbon has a charge of -2. On the right, +4. So you need to add electrons here to bring it down. To go from +4 to -2, that's adding 6 electrons for each carbon. And since I have 2 carbons, that means I need to add a total of 12 electrons to my right side. Now it's important that I make my number of electrons equal in both my reactions, so that way I combine both my half reactions into one full reaction. Because I have 12 electrons here and 6 here, I'm going to multiply everything in my top reaction by 2. So that carries through to all of them. So that gives me 12 electrons plus 28 hydrogen ions plus 2 dichromate ions, 4 chromium ions, and 14 waters. Now I'm going to go ahead and I'm going to add my two reactions together, crossing off the things that cancel out on either side. So notice that I have 12 electrons on the left with 12 electrons on the right, so those cancel out. My species in the middle here, my dichromates, my chromiums, my ethanol, and my carbon dioxide, those are not, so I'm going to go ahead and write those first because those are the meat of my reaction. Okay, so those don't cancel out. Then I'm going to look at my hydrogens. I have 28 hydrogens on the left, 12 on the right. So my 12 are going to cancel out with the 12 here, and that leaves me over with 16 hydrogens on the left. And then my waters, I have 3 waters on the left, 14 on the right. So these 3 are going to subtract from here. When they cancel out, it's going to leave me with 11 waters. So I'm going to have 11 water molecules on the right. Then I can go ahead and I can check my reactions to make sure everything's balanced. I have 16 plus 5 is 21, plus 1 more is 22 hydrogens, and 22 hydrogens here. 2 carbons here, 2 carbons here. 1 oxygen plus 14 gives me 15 oxygens. Here I have 4 plus 11 gives me 15 oxygens here. 4 chromiums and 4 chromiums. So my reaction is balanced.